again, everyone. So I hope you guys are having a good day. So let's proceed to our next lesson of applications of differential equation, which is the Newton's law of cooling. I hope you were able to watch my last video, which is about the growth and decay problem, which is also a application of differential equation. Okay, so moving on. So the rate of change for the Newton's law of cooling, the rate of change of the temperature of the substance is directly proportional to the difference of the current temperature of the substance to the temperature of the surrounding. So I know the wordings are quite confusing, but I help you through it. Mm, we will use now here T as the current temperature. At the same time, it will also act as the variable and the variable. Okay, so Ts will be the surrounding temperature. Is that it? Yeah, that's it. So we have T as the current temperature and also the variable, and Ts as our surrounding temperature. Okay, so the rate of change of the temperature, which is the T. So of course, the rate of change of temperature is also dt. Of course, it must be respect with time. So we'll have here um, dt all over with respect to time, of course, also dt. But of course, we will use a small t. And then it must be directly proportional, okay? Directly proportional to what? Difference of the current temperature, which is also the t, and the temperature of the surrounding. So, so this will be what's the first one? Current temperature. Current temperature is T, and then minus the temperature of the surrounding. So T minus Ts. Okay, so this is our first equation. Now, applying this proportionality sign, you'll have here dt, oops, all over with respect to time. This will be equal to what? We will add here k, or the proportionality constant, times t minus ts. There you go. And then now we have to group the all the variables with, so that we can apply now the integral. So we will have, so this t minus ts must be with this dt, with this dt. So this t minus ts must go down. Okay, so dt all over t minus ts, and of course the dt must go up with the k. It must be equal to k. So we have to group all the same variables, and then dt. And now we can perform the integral. So performing the integral. But of course, we must have a limit for this one. Of course, the limit for this one is the TO, that's from the original temperature or the initial temperature to the final temperature, which is T. We will use T for the final temperature. I hope you guys don't get confused with this. And then for this one, of course, from present to the um, required time that you want. Of course, the present time that must be 0 from T. Okay? And then performing the integral dt over t minus ts, we will have here ln, okay, ln t minus ts, and then to to t, that will be your limit, and this will be equal to k t limits from 0 to t. Okay, so now we can apply the limit. Remember that will be upper minus lower. So ln times ln t minus ts. So applying t first, the upper limit is t, and then minus the lower limit, which is ln times to minus ts. And then this will be equal to k t minus k. This will be your upper limit, the t, and then your lower limit will be 0. Okay, now for the first one, the ln t minus ts minus ln to minus ts, apply the logarithms, properties of logarithms. So you will have here ln, it will be now divided. So t minus ts, okay, all over to minus ts. So this is equal to, of course, this will be 0. Okay, this will be 0. And then you're left with here with kt. Now, if I want to eliminate ln here, all I have to do is just um, take the e of both sides. However, I'm already happy with this form, but you can also do that. Okay, so you can have this one. This is the formula for Newton's law of cooling, or if you want, you can have something like this. So t, if I will, you will take the e of both sides. You can have this one. So you'll have t minus ts all over to minus ts, e raised to kt. So whatever formula that you want. However, I'm more comfortable with this one. Okay. So that will be the formula for Newton's law of cooling. With that, let's proceed to some sample problems. Okay, so let's go to our first problem. So we have a pitcher of buttermilk, initially at 25 degrees, is to be cooled by settling it on a place where the temperature is 3 Celsius. So suppose that the temperature of the buttermilk has dropped to 15 Celsius after 20 minutes. So from 25 it became 15. When will it be 5 Celsius? Okay, so let's put all the givens first. Okay, so we have given um, we have initially 25 Celsius. So we have TO, which is the, I'll be using, this will be the symbols that I will use. So TO is your initial temperature. T is your final temperature. Temperature, of course. T is your time. K is the proportionality constant. And what else? I think that's it. Oh, TS. TS is your surrounding temperature. Now, going back to the given, we have TO, which is the 25 degrees, and then settling on a place where the temperature is 3. So we have the surrounding temperature, which is 3 Celsius. And then suppose the temperature of the buttermilk has dropped to 15. So that is from 25 it became 15. Therefore, your final temperature will be 15 Celsius. How many time does it? It takes 20 minutes. It takes 20 minutes. So the we are required to find when will it be t must be equal at t no, we are required to find when will it be, therefore we are required to find the time. Okay, so this must be either in minutes, can be in minutes, at the final temperature must be equal to 5 degrees. So these are degrees, okay? I wasn't able to put the symbol for the degrees, which is the small circle, because I cannot type it. I cannot type that, but I hope you get that. Okay. So let's try to answer this. So answering this, of course, we'll have the formula. So let's see. So the formula will be I'll just try ln times, this will be t minus ts all over TO minus TS, and this is equal to KT. Now applying this first, this is the first condition. So remember again, the purpose and the sole purpose of the first condition is just to find the value of k. So let's use the first condition to find the value of k. So ln, using the first condition now, ln times, so t is 15. So we have here 15 minus ts is 3. And then to is 25 minus 3 again. And this is equal to k. And then your t is 20 minutes. 20. Okay. Therefore, we can say that k is just equal to ln. This is 15 minus 3, that's 12, all over 25 minus 3 is 22. Okay, all over 20. Or we can also have here ln, that's 6 over 11, right? Lowest term, 6 over 11, all over 20. So that's the value of k. So we already have the value of k. Let's try to use this one, the second condition. Okay. So again, using the formula again, you'll have your ln times, what's the value of t? T is 5, right? 5. So 5 minus the temperature of the surrounding is still 3. And then TO was the initial temperature. Initial temperature is still 25. So we have here 25 minus 3 equal to the value of k is this one. So we'll have here ln 6 over 11 all over 20. And the one that we are looking for is t. Okay, so finding the value of t. Okay, so let's try this out in our calculus. So all you have to do, let me try to simplify this one again. So simplifying this one, you'll have here t will be equal to this is ln times, this is 2 all over 22, right? 2 over 22, or 1 over 11. Okay, 1 over 11. 1 over 11 all over this one, ln times 6 over 11 all over 20. So let's try that out. Ln 1 over 11 all over ln 6 over 11. No. Okay. So the answer that I got is that 79.12. Okay. So the answer that I got is 79.1207. 1207 minutes. So it will take the substance to cool from 25 up to 5 Celsius, considering that the temperature of the surrounding is 3 after 79 minutes. Okay, so I think we can proceed to our next. Oh, before I forget, you can also do this. Let's say that, ano, I think I can just present this to the next problem. Okay, so I'll be showing an alternative solution for the next problem. So let's go to our next problem. Okay, so let's have our next problem. So for our next problem, of course, we have to put down all the givens first again. So we have the given. A certain substance can cool itself from 100 to 70. So we have a initial temperature of 100, 100 Celsius, and then 70 Celsius for the for the final, which is T, 70 C, in 15 minutes. So T must be equal to 15 minutes. And then if the Earth's temperature is 30 degrees, therefore that will be our surrounding temperature. TS, surrounding temperature is 30 C. How long will it be? So we are required to find what? Required to find how long will it take to cool from 100 to 50. So of course, the for the second condition, we still have the initial temperature is from 100 to 50. Therefore, your initial temperature must be 100 and your final temperature is 50. So 100 C and your final temperature is 50 C. We are asked to find the time. So how long will it take? This must be in minutes. Okay, so let's proceed to our solution. So for the solution, of course, we still have the same formula. So this is the formula, right? T minus Ts, and then To minus Ts equal to KT. So this is the formula that I was able to derive earlier, right? Now, let's try this a different approach. Now, for some reason, okay, so for some reason, you get confused with the formula, okay? Let's say that you get confused on the formula. So instead of T minus Ts on the numerator, you interchange it. You got it wrong, okay? Let's say that you got your T O minus Ts and then T minus Ts. Okay. So let's say that this is the formula that you will be using. I know it's wrong, okay? Because you got TO and T in interchange. Okay? But I'm already telling you it's fine. Okay, you will still get the same answer as long as you are consistent. If you will use this formula, you have to use this formula to the end. Okay, you don't want you will not change it. Okay, so let's try to use this formula first. So let's apply the first condition first. Okay, so for the first condition we have ln times what is to. To is 100 and then ts is 30, and then we have here for the final temperature that is 70 minus 30, and then this is equal to k, and then your t will be 15 minutes, right? 15. Therefore we can have here the value of k is equal to ln, that is 70 over 40, right? That is 100 minus 30 is 70. 70 minus 30 is 40. Therefore, we can have 70 over 40, or just simply 7 over 4 all over 15. Therefore, that's the value for your for the k. Then next, let's apply the second condition. Okay? So for the second condition, you'll have ln times, okay, that's TO minus TS, right? So TO is still 100, and then TS is still 30, and then for the final temperature is 70 minus 30, and then equal to value of K. We already have the value of K. This is ln 7 over 4 all over 15, okay, times the T that you are looking for. Okay. So T now is just simply equal to ln. I think this is not 70, right? No, no. Oh, is it 70? No, this is not supposed to be 70. Sorry about that. This must be 50. Okay? So because we're using the second condition now. So this must be 50. Okay? So this will become a 70 over 20. So this is 7 over 2. Sorry about that. And then this will become ln times 7 over 4 all over 15. Okay, so let's try this one in our calculus. We'll have here ln 7 over 2. 7 over 4. And then the answer is we have here 33.5792 minutes. So this will be your answer. Now, if you got confused, let's try to use the right formula. So using the right formula, you'll have here ln, that's t final minus surrounding, and then initial minus surrounding, and this is still equal to k. Yes, sorry, it's kt. Now let's apply the to. Yeah. So applying the first condition, you'll have here ln times the final temperature. The first condition is this one. Okay, this is the first condition. That will become 70 minus 30 all over 100, which is the initial temperature minus the surrounding 30, and this is all equal to k times 15, right? 15. Therefore, you'll have here the value of k now will be equal to ln. That's 70 minus 30, that's 40 over 70. So we can have here 4 over 7 all over 15. Okay. And then applying to the second condition, that's ln times, remember that we are using this formula. Okay. So your final must be 50, 50. And then temperature, surrounding temperature is 30. And then this one you'll have here the initial, which is 100, and then minus 30. And this is equal to whatever the value of k. This is the value of k, and then times the t. So therefore, we can say that t is just equal to ln of 2 over 7, right? That is 20 over 70. That's 2 over 7. And then your value of k is ln 4 over 7 all over 15. Okay. So if you will try out in this one to your calcu. Okay, so let's try this out in the calcu. So this is ln 2 over 7 and ln 4 over 7. As you can see, the answer is 33.579 minutes. So I hope you were able to get my point that it's okay if you get if you interchange the T and TO of their positioning on the formula, and all you need to do is you have to be consistent in using that. So if you will use the one formula, whichever formula here, you have to be consistent using it to the end. So I hope I was able to help you guys again, especially during these online classes, and I think that's it for this video. So if you have any question for this one, so of course don't hesitate leaving a comment down below. I'll be happy to answer everything, every one of it. I always read all the comments in my videos. And thank you all guys for watching, and of course don't forget to subscribe and hit the bell notification so that you will be updated or notified as soon as I upload a new one. So thank you everyone, and I'll see you on the next one. Bye bye.